could see by my screen that you were talking, so that must mean you can hear me. I can't hear you though, so sorry if you need anything. While we're having a lecture, I won't be able to hear you. Unless I can fix it. We'll see. All right, let's see here. Please, 8. Oh, by the way, I am recording, just so everybody knows. Usually most people don't care, but if you happen to be shy about having your voice being recorded, I guess you want to know that. Anyway. Okay. Does everybody know who was here first? When I get to you, get a little bit of extra credit for being here first. I don't always do that, but today I am. All right, let's see here. And then we have Esterson.
Yes,
All right,
I got red on.
I'll count that. A little extra credit for Red, supporting the troops on Friday, if you happen to support the troops. Let's see. Said James is online. Last name, wait. First name, Grace. Good. And then we also have a key online, assuming I'm pronouncing that correctly. Just a reminder for those of you guys online, throughout the lecture, I'm going to give attendance words, and then you need to send me those attendance words before 9 a.m. to get your extra credit and to be counted as present. Anyway, let's see. So, first one here, who gets a little bit of extra credit. Boggs. Hey. Do we have Bonner in the back? Sweet. Okay. Oh, I know this one. Wilder, right? And you're wearing red, so a little bit of extra credit for that. Two. Guys left.
Listen, in your defense, I haven't been here before.
Oh, that does help. Oh, okay. Now I have a much smaller pool to choose from. Okay, Morrison.
Yeah.
Wait. But we've been in touch.
Yeah.
Okay. I really am sorry about that. About the whole
No, it's okay.
completely out of my control. Even out of Dr. Collins, who's the department chair. It's out of his control too, but he just knows more. That's why I referred it to him. At least hopefully this batch should be easy for you, since you've already got the stuff, right? You're just
Yeah.
basically in it for the lab, but unfortunately you do this stuff too.
Yeah.
So what you've missed out on, well, I think I've sent you the emails, but make sure you check your emails, your WBSU emails, because I should have sent some for Monday and Wednesday. There's videos that you should watch and answer questions for attendance. Thank you for letting me know. Good morning. Let's see. Is it Wilcox in the back?
Yes.
All right. Are you wearing a red shirt?
Yes, I am.
All right. A little extra fit. It's Friday. So we only have one person unaccounted for right now. Let's see. Do this. We have Noah King by any chance? Hey.
Good morning.
Morning. Okay. Not Velo or Blount, because they haven't been here and I don't know what they look like. Probably not Clayton. They haven't been here yet either. I think I talked to Dawson, and I don't think either one of you are Dawson. Mm-hmm. Mm-hmm. Green?
Yes.
Green with a red shirt. What do I credit with that? Henson? Okay, all right. Henson in red for the extra credit. Let's see. Didn't lose here yet. Yes. Rice in the middle, correct? No? I think Rice was sitting there last time. Board. Okay, all right. We only have a minute, so my guessing game will come to an end soon. Anyway, award is red, so that's a little extra credit. So first name Grace? No, don't tell me, please. I'll try to guess. Last name Ellis? Hey. Okay. So far, everybody's accounted for, right? Anybody not been called? Nice. Maybe less than a minute. So let's do some reminders. Oh, Paula, right?
Yeah.
And it is 8. All right. So I'm gonna do announcements, reminders before we get started. Let's see if anybody comes in for 8:01. Let's see. So don't forget your pre-labs are due tonight. And I'll take your question in a second. So far, not many people have turned it in. I'd say about 50%, or to rephrase that. As far as I can tell, so far, only a handful of people have tried it. And of those handful of people, only about half of them know how to do it, and the other half need my help. Some of you haven't returned my emails who need help, and I've said, hey, let me help you. So, please, if you haven't taken a look at the lab yet, take a look at it when we leave as soon as you can, because you might go to a class next, I don't know. But take a look at my lab, or the lab as soon as you can, and let me know if you need help. The lab itself isn't that hard, I don't think. Like the questions, it's just the whole logistics of like, how do I make it my copy? How do I turn it in, right? So let me help you, because my office hours, my office hours are over at noon, and I should be available after that. But just in case, let's just say I won't be available after noon. So if you need, take a look at it. So if you need my help, let me know. Also, I would really like to make a video to show you how to do it. So I will give anybody 5 points of extra credit. One person I think did say they would do that. So we'll see if that comes to fruition. But I would like to sit down with somebody online so they can share their screen through the process and say, first you do this, second you do that, and then we'll record it, and then I can share it with you guys and then my future students too. So 5 points of extra credit for that. But again, I do have somebody who's said they would do that. If that doesn't fall through, or if that does fall through, then I'll let you know, and then maybe someone else can do it. Any questions about that? Okay. Long story short, the pre-labs are turned in by sharing them on Google Drive, and the labs are turned in by uploading them to WVSU Online, right? So you shouldn't have anything uploaded to WVSU Online. Again, that's long story short. So if you need more help, meet me for office hours. Meet me online. Online would be better in this case, because it would be helpful. I can see your screen, or you could come to my office, but it'd be more helpful in that online. If you don't remember how to meet me online, just shoot me an email, right? Start typing the weird name, Vasilios Dianelos, right? I know it's hard to remember, but kind of remember it and start typing it, then hopefully my name will come up. Yes, ma'am.
Where's the pre-lab at?
Good, pre-lab. So if you look at that first announcement, remember I sent an announcement that said, make sure you read this. Part of that announcement, and I remember I also said, make sure you read all the clicks, or click all the links. Towards the bottom of that announcement, this is just one of the many ways you can get to the lab. Towards the bottom of the announcement, there's a link that says all the due dates for this semester, or something like that. If you click that, then a little spreadsheet will come up with every single assignment and every single due date. And every single assignment has a link to it. So you just click that link and it takes you to the lab. Make sense? Good. And again, if you still need my help, meet me online. We'll figure it out. The first week's the hardest, because you're not just learning how to do the lab, you're learning how to turn it in and all that rigmarole. Anyway, it's past 8, so let's get started with attendance. Dawson, I can't get back to that. Okay, Key is online. Do we have Belo, B-E-L-O, last name B-E-L-O. Last name Blount, B-L-O-U-N-T. All right, neither one of those last two are here. Boggs is here, Bonner is here. How about Clay? Last name Clay, not here. Last name Clayton, not here. Dawson is online, and I'll remind you, if you're online, once I do after the class, send all the attendance words sometime before 9 a.m. to get your credit and be marked as that present. Ellis is here. Paula is here. Green is here. Harrison is here. Henson's here. Last name James is online. Kesterson is here. King is here. Lewis is here. Linda Q is here. Morrison is here. First name Grace is here. And wearing red, so that's a little extra credit. Same with Linda Q. Last name Rice is here. Ward, Wilcox, Wilder are all here. Anybody didn't call? All right. I think that's it for the announcements and reminders. Also, independent work. Remember, it's worth 20 points per page until today. Normally, it's worth 10 points per page, but to encourage you to start writing independent work, I set it up to 20 points per page until the end of this week. So just write one paper. Please, write one small paper. Think of a biology question and go answer it. It's pretty simple. My favorite food is, I don't know, whatever. I really like green apples. I'm wondering where they're from. I looked it up, and according to applelocator.com, they're from wherever, I don't know, whatever you can think of a question. Because some of you have turned in independent work, thank you, and like one of you had, like I say, so far everybody's had some issues. And that's okay, because it's the first one. So you send it in, teach you how to do it, send it back, and then we figure it out. But now's the time to start figuring those out, and not later in the semester. So any questions? I think that's all the reminders and announcements I have. If you're on the Facebook group, you know that I was hoping to have a hike, an extra credit hike today at noon at Wine Cellar Park, but so far only one person has RSVP. So unless we get another person, then we're not going to do it, just because I feel like it's inappropriate for me and one other student to be out and about by ourselves. So if you're interested and you're not on Facebook, shoot me an email and I'll give you the details. But today at noon, we're leaving Hamlin Hall. And again, I'll give you the details. Does anybody have any questions about anything before we get started? Nice and easy. All right. Today, hopefully we'll finish this boring chapter. I really do not like chapter 1. It's necessary, I guess. To me. Who knows? This might be the most exciting one for you. Anyway, let's jump into it. We finished 1.1, where we talked about the themes and concepts of biology. Now we're going to talk about the process of science. So remember, big picture here, biology is this scientific study of life, right? So the first portion of the chapter, we kind of talked about what life is, right? And now we're going to talk about what the process of science is. So let's jump into it. Here's the learning objectives. I know they're probably a little bit hard for you to read. But in theory, by the end of this section, you should be able to identify the shared characteristics of the natural sciences. I might or might not ask you questions about that on the exam. You should be able to understand the process of scientific inquiry. You do need to know that, specifically the scientific method. I'll talk more about that when we get there. You need to be able to compare inductive reasoning with deductive reasoning. And there might be like one question about that on the exam I haven't determined yet. And then finally, you'll need to be able to, and we'll talk about it when we get there. And then finally, you need to be able to describe the goals of basic and applied science. And I almost guarantee you there won't be any questions about that on the exam, but I teach out of the textbook, so here we go. Any questions before we get started? Occasionally, I'm going to need to check back with the online thing to make sure it hasn't kicked me off like it did yesterday. That was annoying. Speaking of online stuff, the first word for attendance will be knowledge. Knowledge. So again, if you're in person, you can write those down if you want, and then send them at once at the end, one email please, with all the words, sometime before 9 a.m., and you can get extra credit. For those of you who are online right now, not watching the video, but watching the live stream, you need to send those words before 9 a.m. to get your credit. All right, and then of course, if you're watching the video, who knows? Maybe I'll have you send the words, maybe I'll have you ask questions. But anyway, here we go. Science. What is science? Well, first of all, it gathers knowledge about the natural world. You should know that. Or a better way of describing it that your new textbook doesn't describe it as, but I do. So take notes. You're a note taker. It is the inquiry-based effort to describe and explain nature. That's what science is. That is the definition of science that I might ask you on the exam. I'm going to put a little question mark next to that. You know what? I'm going to put a small question mark. I think I probably will ask you that on the exam. Technically, the exams are written, but every semester I go in and make a few changes. But yes, you need to know that science is the inquiry-based effort to describe and explain nature. Discoveries that are made by a community of researchers, science consists of discoveries made by a community of researchers because it's a social enterprise, meaning we all kind of like, what's the quote? I forgot who said it because I haven't drank enough coffee yet. We're all standing on the giants' shoulders, basically, right? So every scientist now who comes out with any kind of big breakthrough, it's because they are going off of what other people discovered before them. Of course, that bullet point's not really important as far as the exam is concerned, so I put a little X next to that. Methods include observation, record keeping, logical and mathematical reasoning, experimentation, submitting conclusions to the scrutiny of others. I'm going to put an X to that now But we will come back to all that. That's just kind of like an introduction to what we're going to talk about in greater detail later today. And then you won't need an X, because I probably will ask you some things about this, but again, we'll talk about it in more detail later. And all of these are about to be discussed, right? So everything on that list we're about to get into a little bit deeper. So any questions about this whole introduction before we start digging deeper into all these little things? All right, there's another definition of science that you should know. It's defined as knowledge about the natural world. So that's how your textbook defines it. So again, if you're taking notes, like I said in that previous slide, that's the way I like to define it. So you should know that version, but you should also know this version. But in short, when you think of science, you should think of like learning things, discovering things, figuring things out. And you should also think about the natural world, right? The natural world. So we're not talking about religious things, right? So religion and science kind of in different realms, and we'll talk about that later. Science requires observations that can be confirmed and measured. So, for example, we can't say, like, scientifically, I can't say that there's a werewolf on the dark side of the moon. That's a bad example. Some place that we haven't been yet, I don't know. Certain places at the bottom. Okay, how about this? Well, science cannot say that the Loch Ness Monster does not exist in certain places in the ocean. I mean, surely it doesn't, but we can't confirm that unless we've seen all the places in the ocean. But we'll talk a little bit more about that later. But again, for science, it has to be, these observations have to be confirmed and they have to be measured. So yeah, I guess another good example is if a guy's out in the woods in West Virginia and says, I saw Bigfoot, makes that claim, that's not really science yet. That's just one person. That observation has to be confirmed by others before we can call that science. Anyway, science is also subjected to repeated testing. Maybe not in this class, right here, you do a lab, you answer some questions about it, you're done with it. But in real science, when you're doing experiments and you're presenting them to the public, then they will usually be tested, right? Repeated testing. Here's the part that I like. Science cannot be applied to purely moral questions, cannot be applied to aesthetic questions, cannot be applied to spiritual questions, right? That's not the realm of science. And there's nothing wrong with trying to figure out moral questions and aesthetic questions and spiritual questions. There's nothing wrong with that. There's just different ways of figuring things out. Science deals with the natural world, so we don't deal with those things. We shouldn't. But don't get me wrong, science often deals with moral questions, but doesn't really answer moral questions, right? So we talked on Wednesday a little bit about scientific ethics, right? So we use ethics in science because we should, but it doesn't necessarily mean that we can use science to answer moral questions. And if you've had my Bio 108 class, that first discussion that we have of the semester is a great example of that. Like, should we use coal to make electricity, right? That's a moral question. And look at the pros and cons. There's facts that tell you here's how burning coal is good. There's facts that tell you how burning coal is bad. And then it's up to you to decide if you like it or not. That's a moral question. That part's not the scientific question. Anyway, we'll talk a little bit more about that later. Any questions so far? All right. So these next terms are things you definitely need to know for the exam. I'm going to talk about all three of them, and then we're going to come back and talk about hypothesis again later in context, because hypothesis is one of the steps of the scientific method. And again, we'll talk about that later. But for now, let's just talk about kind of the relationship between these three words. A hypothesis, as you need to know for the exam, is a suggested explanation for an event. That's one way of putting it. Another way of putting it is a tentative answer to a question. There's all kinds of ways you can describe or define a hypothesis. And basically, you need to know, again, this is like, it's answering a question, right? You're answering a question, and we're going to talk it again. We'll talk about it a little bit later. Has to be testable and falsifiable. So again, I could say, there's a planet that we haven't discovered yet in the universe that is filled with werewolves. That's not a hypothesis because we can't test that or falsify it, right? When I did write this, though, because usually when people grow up, they hear that a hypothesis is an educated guess. It's not necessarily true. It's sort of true, but I don't like that explanation. because again, that doesn't get in far enough to say it needs to be tested and falsified. And you should be able to test it. You should be able to say, no, that's not true. And your textbook goes into detail, but that's basically what you need to know for the exam. Any questions about hypotheses? All right, scientific theory. I like this. This is really important. It's generally accepted scientific theory has been thoroughly tested and confirmed, and it's an explanation for a set of observations or phenomena. So it's different than a hypothesis. Like a hypothesis, it's a question that can be tested, but a scientific theory has already been tested, thoroughly tested. It's been tested more than once. Scientific theories are the foundations of scientific knowledge. And again, your textbook goes into a lot of it. And in the next slide, I'm going to really go into, or the following slides, I'm going to really go into the difference between these two things. So for now, I'm just going to leave it at that. But you will need to know the difference between the two. They're not the same. And of course, in common language, people use these terms interchangeably, and that's not correct. Like people use the term theory when they don't mean theory. So say, hey, I wonder why my car is making this noise when I drove it to school. Someone would be like, well, I've got a theory. It's probably this part. That's not a theory. That's a hypothesis. So almost always when you hear someone say in common language, I had a theory, usually they mean hypothesis. It means they have an explanation for something that you could test. But it's not a theory, because a theory has been tested and it's already been supported. Which brings us to scientific laws, and those are the things that we won't really deal with too much in this course. But scientific laws are often expressed in mathematical formulas, sort of like the law of gravity. By the way, and you can look this up for independent work if you want, there's a difference between the law of gravity and the theory of gravity. You can look that up if you want, you don't need to know it. But as you can tell from this table, or from this information here, the law of gravity includes the mathematical formula for gravity. Theory of gravity, it's different. Again, you can look it up if you want. Anyway, scientific laws also describe how nature will behave under specific conditions, right? Again, the law of gravity is a great example. We know if I drop something, we have math to tell you how long it's going to take before it hits the ground. Anyway, any questions about this? Can't wait to be done with it. Again, to me, this is the boring stuff, but it is necessary to understand before we jump into really jump into biology. All right, let's talk a little bit more about theories. A theory is a comprehensive, well-substantiated explanation that is broader in scope than a hypothesis. So like I said, I'm going to kind of get back into this discussion about the differences and relationships between a hypothesis and a theory. By the way, this stuff's not in your textbook. So if you're taking notes, you might write this down and say, hey, even if you don't write this down, you can at least write yourself a note and say, hey, there's a part of the PowerPoint where he's presenting information that's not from your textbook. So if you're going to study it, study the PowerPoint. Anyway, yeah, so again, for the exam, this is a very important bullet point. Theories are comprehensive, well-substantiated explanation, and I put in bold because the question might say, hey, what's the difference between a theory and a hypothesis? Theories are broader in scope than a hypothesis. They're bigger. They answer bigger questions. A hypothesis, right, is very specific. It answers a very specific question. A theory answers a big question, and from that big question, you can have a lot of smaller questions. And we'll talk about that in some future slides. But for now, I'll leave it at that. Theories are only widely accepted if they are supported by a large, varied, growing body of evidence. So the theory of evolution, again, isn't just some guess. So something like, yeah, that's probably true. No, it's been tested a lot, and it keeps getting tested. And the body of evidence grows. Theories are used to explain many observations, unlike a hypothesis, right? This is why a theory is broader in scope, because a hypothesis aims to explain one observation, right? A theory explains many observations. And then also, a theory is used to devise new and testable hypotheses. And I'll give you some examples for that. And like any scientific idea, theories must be refined or abandoned if new contradictory evidence is discovered. Also a great independent work topic if you're into it. What are some scientific theories or hypotheses that have been debunked? Right? It happens, right? That's the beauty of science. We don't ever say we're right. We say, based on all the evidence, this is what we know. And then as the evidence changes and technology changes and we have better tools to measure things, then we sometimes find out that what we previously thought was wrong. then it has to be changed. That's the beauty of science. Anyway, all of this, again, this whole page basically sums up to say this, right? It's comprehensive, right? So it covers a lot. It's well substantiated and it's broader in the scope and hypothesis. All these bullet points kind of boil down to that one bullet point. So if you're studying, this is the bullet point you need to know. All right, hey, we're still recording. Amazing. Anyway, so the next word for attendance, let's change it up a little bit. This time I'm going to circle it instead of say it. So if you're online, you've got your eyes closed, and you're relaxing, and you're listening to the lecture, which is completely acceptable, open your eyes and look. This is the next word for attendance. And again, send them all in one email before 9 a.m. That's a mandatory thing if you're watching the live stream. If you're here in person, that will be a little extra credit. Send them before 9 a.m. and please send them in one email. All right, any questions about this slide before we really get into like talking about how a theory and a hypothesis are related? I'm gonna give you an example. All right, and again, this is an example, so I'm gonna put a big old X through here. Meaning, I'm not gonna ask you any specifics about anything I'm about to tell you. I'm just trying to help you understand how these two things are related. So here are two hypotheses, seemingly unrelated hypotheses. One of them says, long, thin roots are an adaptation that helps some plants survive in an urban habitat, right? So here's a picture of a little tree that's growing between a lighthouse wall and pavement, right? So the question may have been, well, how's that tree growing there? I thought trees need soil. And then the hypothesis to that question could be, well, it's the long, thin roots, right? It's an adaptation, helps them get in there. And then there's another hypothesis. I need another picture up there, but there's no picture for this one. The unusual bone structure in hummingbirds' wings is an evolutionary adaptation that provides an advantage in gathering nectar from flowers, right? It allows them to hover and get the nectar from flowers. That's got to be hard for a normal bird who just flies around and can't hover, right? So the question may be, hey, how do hummingbirds do that? And the hypothesis would be that, right? So here we have two completely different hypotheses. One's about plants, one's about birds. So in contrast, the following theory ties these hypotheses together. Adaptations to the local environment evolve by natural selection. And again, that's just an example. We'll talk about natural selection later in the semester. The point here is the theory of evolution by natural selection. It provides many, many hypotheses, right? And to this day, people still use this theory to test very specific hypotheses. And of course, if they get that hypothesis wrong, that doesn't necessarily mean that the theory is wrong, right? So maybe this hypothesis about the roots is incorrect. Maybe there's something else that's causing that tree to be able to thrive where it is. That doesn't mean natural selection is wrong. Maybe it evolved some other function other than thin roots. Anyway, any questions about that? We're moving along quite nicely here. Another word I think you should know. I'm not quite sure if I'm going to test you on it. Again, this is not your textbook. Let's talk about what a fact is. A fact is a piece of information that is considered objectively true based on all current evidence. So you might need to know that for the exam. It's something you should know in life anyway, right? A piece of information considered objectively true based on all current evidence. So, for example, I could say as a fact that, what's the name of that Mexican restaurant? We could always call it Mexichones. Los Agaves, right? I could say it's a fact that Los Agaves is 3.2 miles from here. I'm not sure if that's how far it is, but it's probably close. But that is objectively true. Let's pretend that my numbers are correct. I think they are. But anyway, that could be considered objectively true, right? But what I couldn't say as a fact is say, you know what, the best margaritas in town are at Los Agaves. That's not objectively true. That's subjectively true for me. I might really love the margaritas, but it's not objectively true because it's an opinion. A fact can be verified, therefore it's different from opinions. Right? I can verify that Los Agaves is 3.2 miles from here, or whatever it may be, right? You can verify facts. A lot of people associate facts with science, which is good. That's kind of correct. But the accumulation of facts is not the primary goal of science. And the example I use is my thesis work for my master's degree. I was looking at plants to see which genes are responsible for the trichomes. I don't know if you guys know what trichomes are. These little fuzzy things. It's the things that make plants fuzzy. And I was looking for the genes that are responsible for that. So to do that, I had to sequence a lot of genomes, right? A lot of different plants. I took out their DNA, took out their RNA, sequenced it. And those were a bunch of facts, right? I had spreadsheets upon spreadsheets of facts. Like this plant used this gene this much. That plant used this gene that much, right? Just pages of facts. But those facts didn't mean anything until we put them into context, right? And that's the cornerstone of science. The explanations that apply to the greatest variety of phenomena, right? So basically what I'm saying here is facts by themselves are useless. But then using those facts to understand something or to answer a question, right, like a hypothesis, that's what we're after. So facts are important, but facts by themselves are useless. So keep that in mind when you're in lab. When you're doing experiments and you're taking data, those are facts, right? But the data itself is useless. It's up to you to analyze that data. What is the data telling you? Is it answering your hypothesis, or is it supporting your hypothesis, or is it not supporting your hypothesis? All right, any questions about facts? All right, another example here. This is from your textbook, but I like that your book pointed this out. Here's some really famous scientists, right? We've got Newton, Darwin, Einstein. Not that I'm going to test you on that. And I like that they said that they stand out in science not because they, collected a lot of facts, right? They're famous because the things they figured out had broad explanatory power, right? So it's not all about collecting facts. Any questions about that? Relatively unimportant slide as far as the exam is concerned. All right, let's talk about the natural sciences. I might ask you what a natural science is. I'll put a question mark next to this. These are the sciences that are related to the physical world and its phenomena. It's all about the natural world, right? So natural sciences, as opposed to like social sciences, for example, like psychology. You can think of natural science as kind of like what you would see in a natural science museum. It includes biology, astronomy, physics, chemistry, math, geology, etc. And I put a big old X through that because I will not be asking you all the different types of natural sciences. If anything, you just need to know that science is related, or natural sciences are related to the physical world, right? Any questions about that? All right. And another reason I'm not going to ask you about this is because, as your textbook points out, there is no complete agreement when it comes to defining what the natural sciences include. So that would also be a good independent work topic, which brings up a good point. And I love that this person did this so early so I can use them as an example. I pose questions every once in a while in lecture for independent work, so you can say, hey, maybe write a paper about this. But what you don't want to do is if I pose a question and then kind of go on to explain the answer to the question, don't use my explanation because I'm already teaching you. The idea of independent work is for you to find your own answers. Or as a critical thinking person, maybe you're thinking, well, I'm not going to take his word for it. I'm not going to take the textbook's word for it. So don't, right? If I tell you something, just look it up. Say, well, I know you already taught us this, and I looked it up, and according to this source, you are correct. Or I know you already taught us this, but I looked it up, and according to this source, they kind of describe it in this way, right? So feel free to do that. That's the idea of independent work. Well, first of all, it's either for you to find something that you're interested in, or in this case, in this context, second guess me, second guess the textbook. But what you don't want to do, again, is answer any question that I pose with information that I gave you, because I want you to branch out, learn how to do a little bit of research. Anyway, some divide natural sciences into life sciences and physical sciences. Life sciences, obviously, you're studying living things, such as biology, and physical sciences are pretty much everything else. So once again, a big old X. I'm not going to ask you anything from this slide, at least not on the exam, maybe on the quiz, but not on the exam. So there you go. Any questions about that? All right. So here we go. 2 methods of logical thinking. So if you download this PowerPoint and click this link, it's a great video. I think it's a great video. It's a great short video that kind of explains what I'm explaining but explaining it in a different way. So if the way I explain it doesn't make sense, maybe that video will help make it sense. But yeah, I might ask you this stuff on the exam. You might need to know the difference between inductive and deductive reasoning. So let's talk about it. Inductive reasoning uses related observations to arrive at a general conclusion. It involves formulating generalizations inferred from careful observations and the analysis of a large amount of data. And in a sense, you're going from very specific things to general things. And again, just to save time, I recommend watching that little video. They give some really good examples. But it takes about, I think, I don't remember, maybe like 5 to 10 minutes. But anyway, that's inductive reasoning. Deductive reasoning is used in hypothesis-based science. And in a sense, it's the opposite of inductive reasoning because it uses general principles or laws to predict specific results. So it goes from general to specific. So using an example earlier, we have the law of gravity, right? So we could take that and predict what's going to happen if I drop something from a certain distance, right? We can figure out how long it's going to take before it hits the ground because we're going from general principles to a specific outcome. And again, I'm going to put a big question mark next to this. I'm not sure I'm going to ask you anything about this on the exam. I think the most important thing to know would be this bullet point right here. If anything, and not even for exams or quizzes, just know of the two, inductive reasoning versus deductive reasoning, we're going to be mostly doing deductive reasoning in this course. So, any questions about that? All right, if you came in late, make sure you email me sometime before 9 a.m. to let me know you came in late so I can mark you down as present. Let's see here, next slide. All right, there are two main pathways to scientific study. Might ask you a question about this stuff, so I'll put a question mark. I will say it's not that important. But anyway, there's descriptive science, which aims to observe, explore, and discover. How many of you have ever heard of somebody named Jane Goodall? Some of you, does anybody remember what she did? Not like specifically or what she wrote or what books or what awards she won, but in general, what did she do? Yes.
Like monkeys?
Yeah, she was hanging out with chimpanzees, or I think it was chimpanzees, maybe gorillas, but anyway, definitely some sort of primate, right? So she wasn't out there trying to answer any specific questions. Generally speaking, she was just taking observations, right? She was learning their culture, writing everything down, all these observations, all these facts, all this data. She was taking it down, but she wasn't necessarily out there trying to like test a hypothesis, right? That was descriptive science or discovery science. Then we have what we're going to mostly do in this course, which is hypothesis-based science. And it begins with a specific question or problem and a potential answer or solution that can be tested, right? So what we're doing in lab is mostly hypothesis-based science. But they're both important. And a lot of times the boundary between the two overlap. So again, going back to my thesis work, like I said, I was trying to find the genes responsible for trichome growth on plants. That was basically, I mean, technically because I was doing an experiment, I had to have a hypothesis. So technically I was testing a hypothesis. But really what I was doing was descriptive or discovery science. I wasn't really trying to, well, I was trying to figure out, the genes responsible for trichome development. So you could say that was hypothesis-based. But my point being, you know what, never mind. I'll come to that on a later slide. I forgot I have a good slide, a better slide for that. Anyway, any questions about this slide? Again, I think the most important thing here is that you would know that we in this course are mostly doing hypothesis-based science. We're not out there just collecting data. Though, for independent work, if you want to do some discovery science, feel free. You might say to yourself, I was just curious, I live next to these woods, and I was just curious to see what the different types of trees were. And I went out there, and there was 15 maple trees and 20 oak trees, whatever it is. You can do that kind of stuff if you want. All right, here we go. This is probably the most important, I think, so far from today. This slide, moving forward, is probably the most important stuff I'm going to tell you today. Not only am I going to test you on it, but to me, this is what we're doing and what I'm trying to teach you. More than knowing biology, you need to know the scientific method. You need to know how to think scientifically and think critically. Now, granted, like we talked about earlier when I showed you that picture of the remote control example from Wednesday, we're not necessarily going to do all these steps in real life, but scientific thinking and critical thinking is so very important, especially right now. We have an election coming up. I don't care who you vote for. I just want you to have an informed vote. So when people make claims about this person or that person, I hope you just don't go, oh yeah, I don't like that person. I bet that idiot did do that. Or, yeah, I like that person. I bet they did do that great thing, right? Use some critical thinking, look it up, do some research. Anyway, here we go. The scientific method. Here's what you need to know. You definitely need to know the steps of the scientific method. You definitely need to know them in order. So much like when we talked about the properties of life, I will tell you this. If you look it up in a different source, you're going to get a slightly different answer because the scientific method is a general guideline, right? So again, a good independent work topic if you want. Here's what I'm telling you need to know about the scientific method. If you're interested and curious, you could look up some other sources. I know you said this was the scientific method, but according to this source, they described it this way. According to that source, they described it that way. Feel free to look it up. Just a general guideline, but here's the way you need to know it for the exam. The first step is the observation for the problem to be solved, right? I keep using the same nasty example because it's nasty, it's gross, and therefore it's easy to remember. So I could observe that when my friends hang out, we're having a bonfire, we're drinking a little bit, playing some music, having a good time, but we don't want to disturb the family, so when they have to pee, I direct them to the same corner in my yard. Make sure you pee there. Don't go inside and wake up the family. I'll get in trouble. And I've noticed over a long time, this is all hypothetical, this isn't really true, but anyway, notice over a long time that the grass in that corner of the yard where I always have them pee, it's really green. It's really nice. It's lush compared to the rest of my grass. So that's my observation. Which leads me to a question. Is urine good for plants? Right? I'm observing this, so I'm wondering, is urine good for plants? That's the second step of the scientific method. Speaking of which, I'll take a step back and again tell you this is a general guideline. So for example, a lot of times, as you might imagine in lab, we don't start with observation. We often start with a question. Sometimes I'll give you an observation, like, here's the question you're going to answer. Here's the things that we've observed to bring us to this question. But generally speaking, in lab, I'm going to pose a question, right? So that's usually where we start with that. So anyway, yes, question. Is urine good for plants, for example? Which brings us to our hypothesis, right? It's a tentative answer to that question that we can test. It could be falsified, right? So in that question, all right, let me put it this way. Let's see if anybody can come up with the two basic hypotheses. You could get really specific. I'm going to pose a question, and I want one of you to give me just one basic hypothesis. Don't get too deep, right? So here's the question. Is urine good for plants? There's only two basic hypotheses. Can someone give me one of the basic hypotheses? Think about it. I'm asking you a question. What is one possible answer? Yes, sir.
No, because of its acidic components.
I like that. So you went even deeper. Let's just focus on what he first said. My question was, is urine good for plants? He said no. That's one of the basic hypotheses. If you happen to send me an email with the extra words today, reminded that you answered the question, you get even more extra credit. So yeah, so here's a really easy question. What's the other possible, really basic hypothesis to the question, is urine good for plants?
Yes.
Yes, exactly, right? And of course, you could get more specific, like he said. You could get really specific and say why it's good for the plants, why it's not good for the plants, or you could say, well, pure urine's not good for the plants, but half urine, half water is, or whatever it is you may come up with, right? But anyway, question is the tentative answer to the question. And again, it has to be testable. So if I ask the question, is urine good for plants? And the hypothesis couldn't be only if God wants it that way. Might be a true statement. I'm not saying it's not. I'm just saying that's not a scientific hypothesis because I can't test that. I have no means of communicating with God and say, hey, is that true? Right? So it has to be testable for science. Again, just because it's not testable and it's not a valid scientific hypothesis doesn't mean it's not true. I'm just saying we're just dealing with science here. All right, here's the other part that you're going to get a lot of familiarity with in the labs. It's a very interesting relationship between a hypothesis and a prediction. For those of you who have my 108 class, you're already very familiar with this, I'm sure. So again, a hypothesis is the tentative answer to a question. A prediction is an if-then statement that basically describes how we're going to test that hypothesis. And in real science, not necessarily what we do, I hate saying it that way. In more complicated science, you usually have multiple predictions for one hypothesis. So when you're testing a hypothesis, you usually don't just test it once and like, oh, that supports my hypothesis. I was correct, I'm done. No, in more complicated science, usually what you do is you keep testing your hypothesis in different ways. So let's give some examples. Again, if the hypothesis is, yes, urine is good for plants. Prediction 1, if I have my friends start peeing in the other corner of my yard, then that grass will be nicer, right? That's one way of testing it. If I grow 10 plants and give some of them pure urine, and give some of them half urine and half water, and give others water, pure water, then I will find the ones getting pure urine are grow the most. Does that make sense? So I'm coming up with different ways to test the same hypothesis, because that's how you would do it. The idea in science is actually to disprove hypotheses. So you test it, and if you didn't disprove it, you try it again and try it a different way. Now, as you'll learn in lab, the predictions are a little bit trickier than that, the way I just described it, but for now, we'll leave it at that. And when we start doing it in lab, then you can start getting some experience with making predictions to test hypotheses. So any questions so far? All right, next is the experiment. So now that you've come up with a prediction, which again basically describes how you're going to test your hypothesis, then you test your hypothesis. That's what an experiment is. It's the actual testing of the hypothesis. And this is a very important thing. You'll probably never, ever, ever lose a point for this in lab or in exams or anything, but I just want you to know, and people are going to make this mistake a lot. When you do an experiment, you don't prove a hypothesis correct. You try to prove it incorrect, and if it doesn't prove it incorrect, then your hypothesis is supported by the experiment. Does that make sense? And you'll make the mistake, and I'll correct you, but I probably won't take points. Because every lab you do, for the most part, you're going to be answering questions by doing experiments. And every one of them, of those, I ask you, was your hypothesis correct or not? Did it support your hypothesis? And someone will screw up and say, hey, it proved my hypothesis correct. And that's not a big deal. You won't lose points, but I will write down, it didn't prove your hypothesis, but it supported it. Yes, ma'am.
Are you saying that the hypothesis is only correct if we proved it to be incorrect? Is that what you're saying?
I'm glad you asked. Now, what I'm saying is you formulate a hypothesis, and the goal technically is to find all kinds of different ways to disprove it. And if you can't find different ways to disprove it, if you can't disprove it, then you say, my hypothesis is correct. But you don't say you proved it. You just say it's correct. And the more times you test it and you can't disprove it, then that's just more evidence that says it's correct. Great question. I'm glad you asked. For those of you who concerned, how do I put this? As great as her question was, and I love that she's deep thinking, you guys don't even need to worry about that. We won't get that deep in the exams. We won't get that deep in lab. When you make any kind of logical errors like that, I'll explain that you're wrong, but you probably won't lose points for it. So if that confused you, what she asked about, put your mind at ease. That's not going to be a big deal for this semester. Great question. Anyway, what else about the experiments? We're going to talk more about experiments today, and obviously in lab, we're really going to talk about experiments. Anyway, yeah, so again, the second part of that bullet point that I just pointed at is basically saying the same thing. An experiment can only support or invalidate a hypothesis. Of course, if you invalidate a hypothesis, that's pretty much set in stone. You can say, I proved this incorrect, but you can't say that you proved it to be correct. Anyway, after the experiment is the analysis. You guys will do a lot of analysis. That's a really important thing. Because even though you're not scientists, except we did have one biology major, even though you're not scientists, again, as a critical thinking citizen, hopefully you'll be presented with data. So again, election season, right? So-and-so may say, this person affected the economy this way. This person affected the economy that way. And somebody might give you some data. So you should be able to, as a critical thinking person, look at the data and see if that's even correct. Look at the data and say, oh, wait, yeah, that supports what you're saying. Or wait a minute, no, that doesn't support what you're saying. I see this all the time on social media. Someone will say something like, oh, I love this person because this is a great thing they did, and they present evidence. showing how great that person is, and then you read it, and I'm like, whoa, you completely missed what I was saying. No, this actually does not support what you're saying. Anyway, analysis is important. In harder sciences, we use a lot of statistics, right? Because sample size is important, and we'll talk about that a lot in lab. But in this 100 level class, we don't use statistics. But I do want you to think about statistics, even though, how many of you have had statistics? Only a couple, so that's okay. Even if you haven't had statistics, you should at least know, and we'll talk about it again a lot in lab, but you should at least know that because we're not using statistics, a lot of our findings are pretty much useless in the context of real science, right? We're not going to prove. You never prove a hypothesis, but we're not even going to get close to truly supporting a hypothesis. And we'll talk about that later. And then finally, the last step is after analyzing is reporting, right? And we'll discuss that later too. But once you've done all your experiments, you've analyzed your findings, and you've drawn some conclusions, then you report it. And again, we'll talk about that later in this PowerPoint, which might have to be on Monday. I'm going a little bit slow. Sorry about that. The next step, or the one thing I want to talk a little bit more about is experiments. And again, there's a better explanation on the next slide. But the one I'm going to show you on the next slide is not from your textbook. This one is. In an experiment, you have to have one or more variables. And you need to know this for lab and for the exam. What is a variable? It is any part of the experiment that can vary or change during the experiment. Then we have something called a control. A control in an experiment does not vary. So I'll give a really quick example, talking about going back to the urine thing. If I had these different groups of plants and some of them got pure urine, half urine, pure water, that would be the variable is the concentration of urine. Did the plants get 100% urine, 80% urine, 70% urine, however I set up the exam or the experiment. So the control in that experiment would be the plants that got 100% water, because they didn't get any urine, right? So the reason you would do that, like what if I grew all those plants and didn't have control and all the plants died? Then I might say, oh, urine must be really bad for plants. But then I grow one that's a control, right? If I had a control in that experiment and they all died, including the one that didn't get the urine, then I'd be like, okay, it's not the urine that killed the plants. Something else killed the plants. Does that make sense? So control doesn't get the variable that changes. It does not vary. And again, we'll get a lot of discussion and experience with that in lab. Anyway, any questions about that slide? Before I go to the next slide, which provides information that's not from your textbook, because the old textbook did a better job of explaining these things. Let's see, the next word for attendance will be test. Anyway, to test a hypothesis, you have to run tests multiple times with one factor changing and all the others held constant. So again, I'm going to present the same information I presented to you on the previous slide, but now I'm going to do it in a slightly different way. In my opinion, a better way. Variables, again, are factors that change in an experiment. So in the example I gave, right, the concentration of urine would be the variable. A controlled experiment is one that compares two or more groups that differ in only one variable that the experiment is designed to test. That's a long-winded way of saying basically what I already said about the urine thing, right? We have more than two groups, right? We got the group that gets 100% urine. We have the group that gets 80% urine, so on and so forth, right? We're testing more than one group. And the variable that we're looking at in that case is the concentration of urine. And then again, the control group. Obviously, that's the group that doesn't get the variable that's being tested, right? It's the control, right? And then finally, the experimental group is the group that is receiving the variables that change. So in that case, all the plants that are having the various degrees of urine would be the experimental group. The group of plants that's getting pure water would be the control group. And there's more to this. This is only part one. So before I take questions, I'm going to move forward. Here's something you definitely need to know the difference. And if you've done your pre-lab already, hopefully you already know this. And if you haven't, you need to know this by the end of today because it's part of your pre-lab. Independent variable is the variable whose change is not affected by any other variable in the experiment. And the dependent variable is the thing being studied and measured in an experiment that changes as a result of the experiment. In other words, the dependent variable is dependent on the independent variable. So in that case, growing plants, right? So the height of the plant would be the dependent variable, and the concentration of urine would be the independent variable. because the way I'm conducting that experiment, I'm saying that it's the concentration of urine that affects how tall a plant grows, right? So in other words, you could say the independent variable is the cause and the dependent variable is the effect. And that is it for the week. So on Monday, we'll come back, we'll finish this chapter, and then we'll jump into chapter 2. Yeah, so Monday we'll probably be covering 2 chapters. Not completely, but the end of chapter 1, the beginning of chapter 2. You guys have a good weekend. Email me those words if you want. Take a look at the pre-lab, please, before noon. That way, if you need my help, you can come to me online and get some help. Whose football team is playing this weekend? Anybody? Just me? All right. Yes. Oh, yes. I got you.